think we're up and running. Well, welcome back. Hope everybody had a good weekend. If I didn't already see you this week. Let's see, we got 8 people here. All right. So we are in week 8, which means we've got a little over 2 weeks left. For this class, it means we have 5 class sessions left. That's it. 5 classes left in 222. So we're coming to the end of things pretty quickly. So let me start with an announcement, which is there's a course being offered in spring, CSE222A. It's a special topics course. Scott Koss is teaching it. It's a course on machine learning. So if you're interested in ML and you know, AI and things related to that, and you have space in your schedule, it's a good option to consider. Students I know who've taken this course before seem to really enjoy it. It's very minimal prerequisites, and I think everybody in here should certainly have the prereqs for it. So check that out. It's CSE222A. It's listed as, I think, special topics, but it's I believe 2 credits, and that's going to be offered in spring. So that's an option to keep in mind. All right, let's start with questions. Any final questions on programming assignment 4?
I think now's a good time to start that.
I don't know. You got a few days. You know, you could wait till Thursday.
Did it on BA1, I think.
Yeah. Let's see. There is no treeinit function, which is because to initialize your tree, you do this. That's really your whole initialization. So declare whatever you want to call your root to be a struct node star, which is what we typed deft in uppercase node to, and an empty tree is just null. So with list init, right, we had this sentinel node in the beginning of a list, and even with a completely empty list with no data, there was still a node, and that node needed to be malloc and initialized and so on. So we had a list init function for that. No such thing with trees. So just initialize your struct node star to null, and then pass that to your add and your search and so on and so forth. And yeah, do the malloc inside the add function. So when you want to add something to your tree, the call would basically look like this: root equals add root, comma, and then whatever data you want to add. So if root is null, this will return, you know, something non-null, which will be a single node. But if root is not null, if it's pointing to the root of an actual tree, this will just go ahead and add something into that tree, and the root you get back will actually be the same as the root that that you started with. Let's see, can we go over printing left node right and node left right? And there's also a left right node. So yeah, tree traversal. And the idea of tree traversal is you've got a tree, and it's got, you know, whatever it has on there, and you want to somehow, you know, print it. And we can print the contents of an entire tree by doing 3 things: printing the root node, printing the left subtree, and printing the right subtree. And that will, you know, by definition, print every node in the tree. We're going to print the root node because we're actually going to print that data value with like a printf statement. And then we're going to call our print function recursively to print everything on the left and everything on the right. So to print the whole tree, billions of nodes, right, you only need to do 3 things: print the root node, print everything to the left of the root, print everything to the right of the root. So these are done recursively, and this is usually just a printf. But there's three orders in which we can do this. We can print the node first, and then the left and the right trees. Or we can print the left tree, and then the node, and then the right tree. Or we can print the left and right trees first, and then the node. And so that's the difference between node left node right, and left right node. It's the n tells you when you actually print the root data. And so, for example, if you wanted to do node left right, how do we print that? Well, printf the data from the root node. That takes care of the n piece. And then we want to print everything in the left subtree, and we want to print it in the same order, NLR, so we simply call NLR root arrow left. That takes care of the L part, and then we call NLR once more on root arrow right to print the right part. And then the only thing missing here is we need a base case, which says if root is null, just return, don't print anything. Otherwise we'll recurse forever. So each of these traversals is basically a 4-line function. A check to see if the root is null, and then some combination of printing the root node data, calling the same function on the left and calling this function on the right. And for LRN, the print would be at the bottom. LNR, the print will be in the middle. Alright, let's see. I'd like to talk more about the delete function, even with understanding what delete is supposed to do. In the many special cases, I have to go over the C particulars, like keeping track of pointers of largest and parent largest nodes. So there's bunch of pieces to deleting, which is why, you know, it's the part I recommend doing last. So there's the recursive piece, first of all, which is if you're trying to delete something that's not the root of a tree, we're just going to use a recursive delete function. So, you know, if this is the number 40 and we're trying to delete 20, all we're going to do is call delete on the left subtree, because we know that 20 will be somewhere to the left of the root, and then we're going to set the root's left child to be whatever delete returns. So that's the first piece, and that's the easiest piece to implement, right? So if our data is smaller than the root, then you'd say something like, you know, root arrow left equals delete root comma, you know, 20 or whatever. And if the number or thing you're trying to delete is bigger than the root, then you do the same thing, but you delete from the right subtree, and you set the root's right child to be that tree with the deletion done. So that's the recursive part. That's actually the easy part in this case. The hard part is the base case, which is if, you know, root arrow data equals the number to delete. And, you know, PA4, these aren't numbers, they're strings, so you have to use your string compare, same as you did in PA3. But when you want to delete the root, that's where we start getting into the interesting stuff. So delete the root of t. And so the algorithm we're using is find the largest number in the left subtree, the largest node in the left subtree, and make that the new root. Okay, that's the one sentence description of the algorithm. And everything else is special cases and details. So our goal, find the largest thing in the left subtree, move that to the root. And there's three special cases. So case 1, there is no left subtree. In other words, t left equals null. So if our tree looks like this and we're trying to delete the root, there's no left subtree from which we can find the largest node. So how do we find the largest node and make it the root? We can't. But in this case, since there's nothing to the left and we're trying to delete the root, we just change the root to be the right subchild of the root. So if there's no left subtree, you know, temp equals root, free, I'll say my free root, temp equals root arrow right. So I'll set temp equal to, you know, the right child of the current root. I'll call my free, which, you know, not only frees the struct node that root is associated with, but it also frees the strings in there, the first, the last, and the plate, because those are mallocs dynamically. So my free has to do a bunch of work. So this frees the root, and then we return temp, which is this node right here. This becomes the new root of the tree. Again, this is the case where there's nothing to the left of the root. So if there's nothing to the left of the root, we're just going to change the root to be this node right here. So that case isn't too bad. All right, the second special case, we've got a bunch of stuff on the right. We've got our root. We've got some node over here. And we've got a bunch of stuff hanging to the left of this, but there's nothing to the right of this left child. And in this case, we know what the largest node in the left subtree is. It's this node right here. So if we say something like temp equals root arrow left, and this is not null, because if it's null, then we're in case 1, right, where t left is null. So if root left, call that temp, we know that's not equal to null, but if there's nothing to the right of that, so if temp right is null, then we're in the second case. Temp is the largest node in the left subtree, which means we want temp to become the new root of the tree. And in this case, what we do to make this the root is we simply take the right child of temp, and we have that point to root's right child. So something like temp right equals root right. Free the old root and return temp. So that case also isn't too bad. When I say not too bad, I don't mean it's simple. I mean there's no looping. It's you know, come down here, there's nothing to the right, so have this thing pick up root's right child as its new right child, return that as the new root, free the old root. Things get more complex in case 3, which is the general case. So we have our root, we have some stuff over here, we have a node over here, and we have some other collection of nodes that look like this. And so the largest node in this left subtree is going to be this node right here. It's what you get by starting at the root of that subtree and moving as far to the right as possible. And so we can seed this algorithm by doing something like this. Let me use previous and current instead of largest and parent largest. So I'll give you a variety of options here. So I'm going to say previous equals root arrow left. That's this node right here. And current equals previous right. That's this node right here. And you should know two things here. First, you're going to check for case 1, which is the case where there is no left subtree. So if we're in case 1, previous is going to be null, right? But case 1, we're going to do something in return. So we know that previous is not null. Case 2, is the case where we have something to the left, right, but it has nothing to the right. So if this turns out to be null, we're in case 1. If this turns out to be null, we're in case 2. Since we're in case 3, neither of these are null. Right, so this is not null. And this is not null. If you don't check for case 1 and case 2 first, you risk segfaulting when you're in here. So we've got previous and current. Current could be the largest node in the tree. How do we know if it's the largest? It'll be the largest when it has nothing to the right. So you could loop, you know, while current right is not equal to null. And what do we do? Move down. Move down this, effectively a linked list. So set previous equal to current, current equal to current right. When you come out of the loop, here's our situation. So at this point, current is largest node. Previous is current's parent. And now you go ahead and you do your fix up. So you set previous right equal to current left. Set current left equal to root left. Set current right equal to root right. Call myFree on the root, and then return current as the new root. And this you know, is a good exercise in GDB, right? So if you're in case 3, right, make sure you get down to the case 3. Make sure previous and current look at these nodes. Go through your while loop. When you come out of the while loop, make sure current is here, previous is here, and then step through the touch up, right? Previous right is current left is root left, current right is root right. Free the root before you return. Make sure your tree looks good, right? Go in and you know, see what your tree looks like. You can call your traverse functions while you're doing this, right? For the sake of debugging, you know, each time you make a change, you could call your in-order traversal, for example, and try to get an idea what your tree looks like, or go in GDB and start, you know, following pointers, draw pictures. Start with a small tree. Probably the smallest tree that will work with case 3 might be something like this. Right, so there's a pretty small tree, and this will force you to, you know, leapfrog at least once, get down to largest and previous, and maybe put something over here to make sure that 12 adopts it on the right. So yeah, delete is by far the most complex piece of PA4. Good news, it's only 15 points. But you should be able to get it to work, you know, if you've left yourself time, a couple of days to work on just delete. I think you can probably get it working. But be prepared to spend some time debugging.
Is the complexity of really why you say in the instructions to not deviate from the from how we talk about it in class, or how we do it in class?
Not really. There's some special cases you can use, but actually coding those would take more work. My tree is bogus here. These are a pretty minimal set of steps that you would use to do deletion. The not deviating from the assignment is, for example, like if your tree looks just like this and you want to delete the root, technically all I got to do is move the root down to the 10, right? But that's not what the algorithm is. The algorithm is replace the 20 with the largest thing in the left subtree, so the 14 should go up here. The 12 should adopt the 13. You can put in an extra check and say, okay, so if the root has nothing on the right, then let's change the root to be what's on the left, right? And it will still delete from the tree, but that's a different algorithm. And I don't want you to do that. I want you to do exactly what we described, which is in all cases, take the largest thing from the left subtree, put that up at the root. The one exception being if there is no left subtree, then just move the root down to its right child. But that's actually a little easier than some of the other algorithms you'll find. The complexity of delete is simply the number of kind of special cases, right? We don't have linked lists with sentinel nodes. This is basically a linked list, but there's no sentinel. So if this list is empty, this is null. If this list has a single thing, it's just got a single node here. If there's a sentinel, we avoid some of those. So it will feel a little more complex than what we did with linked lists. But it's you know, really just sort of keeping track of the recursive piece, and then when you're ready to delete the root, 3 cases you have to check for, and the third one needing this pair of pointers. If you want to make it really, really crazy, then you start talking about balancing. And I still hope we'll talk about balancing next week. But I didn't make that a part of PA4, because then you got to do a bunch of extra stuff. All right, other questions? All right, so we're going to switch topics now, and what we're talking about next will still relate to trees and recursion and so on, but with a slightly different focus. So I want to talk about what's called dynamic programming, and dynamic programming is something we can use to speed up recursive algorithms. So we're going to look at certain problems that can be solved pretty easily using recursion, but for which it's going to be really inefficient to do so. Let's see, pseudocode for height and balanced functions. Yeah, we do have those in lectures. Height of a tree is just 1 plus the height of the largest subtree. So it's 1 plus the maximum of height of root left and height of root right. And if the tree is empty, then the height is -1, so that's your base case. Balanced is T is balanced if T left is balanced and T right is balanced and the height of T left and the height of T right are close to each other. Heights have to be within 1. Or T is null. So there's 2 ways we can determine that a tree is balanced. If it's null, which is the first thing you want to check, or if all 3 of these are true. The left subtree is balanced, the right subtree is balanced, and the heights of the left and right subtrees are within 1 of each other. Recursive call to balance here and here, call your height function here. And height of T is 1 plus the largest of the height of the left subtree and the height of the right subtree. With a base case, -1 if T is null. So first check, see if it's null. If it's not, then calculate the height of the left and right subtrees. Whichever one is larger, add 1 to that and return that. And so these are...
Sorry.
Go ahead.
Is max in the standard library?
No, this is just pseudocode. So, you know, set left equal to this, set right equal to that. If left is bigger than right, return 1 plus left. Otherwise, return 1 plus right. That would work fine. Same thing with absolute value. Don't mess with the absolute value because it needs doubles and all that kind of stuff. But calculate the difference. If it's less than or equal to 1 and bigger than or equal to -1, then you know the absolute value is less than 1. Or write your own absolute value function that returns x or minus x depending on whether x is positive or not. But yeah, don't get lost trying to find a max function. Just do an if statement. So yeah, there's a abs function in standard lib, so you can use that. That's fine. Looks nicer to you than a conditional. Yeah, actually I thought apps was doubles, but it looks like it works with ints, so that's fine. All right. Dynamic programming. So we've talked about Fibonacci series. We talked about it in 215. This wonderful series where each term of the series is just the sum of the two previous terms. And so there's base cases, which says f1 and f2 are 1, and then fn, where n is bigger than 2, is just the sum of fn minus 1 plus n minus 2. So this series starts off with 1 and 1, and then basically you add the last two terms to find the next term. 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, 5 and 8 is 13, and so on. And so this is, you know, an infinite series. It gets bigger and bigger. And it's one of the most glorious series you could find. It pops up all over the place. It pops up in nature. It tells you how many petals a flower can have, how many tiles a pine cone can have, how many spirals you find in the middle of a sunflower, right? The ratios of these consecutive numbers approaches something called the golden ratio. And it's something that pops up in art and in music and in architecture and in analysis of the human form. And it's just, it pervades nature. And it's also related to population growth. And this was discovered several hundred years ago by someone named Fibonacci. He used this as an example of growth of population of rabbits under some simplifying assumptions, and came up with this series. And so it's a very easy function to define recursively, and we can write a piece of C code to calculate this function. Right, so here's how we could write the thing just by saying, let's just add the previous two numbers together. So I'll just, you know, start off with a pair of 1s, and I'll just add the last two numbers to get my next Fibonacci number, print that out, and then I'll just, you know, shift these things down. So the last number is the one I just printed, the second to the last number is what was the last number, and I'll just keep incrementing. And if I run this, you know, I can generate Fibonacci numbers all day. Now they blow up once I get past 64 bits, but, you know, the calculation is trivial. It's just add two numbers together to get the next one. But we can also code this recursively. So here's a function that says, you know, to generate the nth Fibonacci number, just take the n minus first and the n minus second Fibonacci numbers, add them together, and return that value. And our base case is, you know, if n is less than or equal to 2, let's just return 1. So that's this case up here. But to find, you know, Fibonacci 3, it will basically calculate Fibonacci 2 and Fibonacci 1, add those together, and return that value. And this works perfectly. There's the start of our sequence. But it gets really slow. Long, unsigned, definitely. So this thing is dragging horribly now, right? And, you know, to calculate the 46th Fibonacci, all you got to do is add those two numbers together. Well, I mean, you know, that shouldn't take this long, but it's you know, a huge delay. And now if we just add those last two numbers together, right, which would be, you know, something that ends with like a 5073, you know, we could have done this in our heads by now. And this poor machine is still, like, grinding out. There we go. So the problem is that when we have this recursion, this recursion branches out. So the effect is, you know, to find the 5th Fibonacci number, we need to calculate the 4th and 3rd Fibonacci numbers. To calculate the 4th, we need the 3rd and 2nd. To calculate the 3rd, we need the 2nd and 1st. These are base cases. We don't have to recurse to find those. To find the 3rd, we have to find the 2nd and 1st. Those are base cases. But we're doing a lot of work, right? We're calling our fib function with the number 2 here and here as well as here, and the number 1. And if we want to find the 6th Fibonacci number, well, first we have to calculate the 5th Fibonacci number doing all this work, and then we have to calculate the 4th Fibonacci number, which requires us to find the 3rd and the 2nd. And the 3rd requires the 2nd and the 1st. And the 2nd is a base case. And so we're starting to do a bunch of recursive calls over here to find f of 4. And now if we want to find the 7th Fibonacci number, we do all of this work to find Fibonacci 6, and then we have to find Fibonacci 5, which is going to be all of this work hanging off of here. And so the amount of work we have to do, the number of recursive calls we have to make to calculate the nth Fibonacci number is increasing as n increases. And in fact, the amount of work we have to do to calculate f7 is the amount of work we have to do to calculate f6 plus the amount of work we have to do to calculate f5. And so the number of steps in our Fibonacci series is actually described by a Fibonacci series. So let's take a look at that. So here's my same Fibonacci function, but I'm using, you know, a global variable here called count to count how many times I call the Fibonacci function. So I initialize it to 1, I call my Fibonacci function, and then I'm going to print out, you know, the number n that I'm calculating, the result of that, right, the nth Fibonacci number, and the number of times I called the fib function. And my fib function, you know, if n's less than or equal to 2, I'll just return 1. That's my base case. Otherwise, I'll go ahead and I'll recursively call my Fibonacci number twice, return the result, and I'll bump up my counter. And so if I run this function, right, it's calculating my Fibonacci numbers correctly, but the number of times I'm recursing is also the same as the Fibonacci number I'm trying to calculate. And so as these numbers grow, the amount of work also grows. And these numbers, you know, nominally, you know, more or less kind of double. There's some multiplicative factor. It's not exactly doubling. It's like 1.57 or something. It's that golden mean. But it's that geometric growth, you know, that's so horrifying computationally, where it's taking something like, you know, 2 to the n operations to calculate the value of n. So this is just dragging like really badly, and it's you know, never going to get to 100. It's going to take way too long. It's rolling over because I didn't use longs here, but it's still, you know, doing the same amount of work. And so this is a problem, right? And the problem comes from this calculation tree. So we can call this a recursion tree or a call tree. And it shows, you know, how our recursion is playing out. If we want to calculate the 7th Fibonacci number, we have to call our Fibonacci function with an argument of 6, which will require calling it with an argument of 5 and 4, and the 5 will require 4 and 3, and the 4 will require 3 and 2, and so on. And when we're done with all of that, then we need to calculate the 5th Fibonacci number over here. And so to calculate that, we have to calculate you know, the 4th and the 3rd, and so on. Someone said, let's take a break until we get to the 55th Fibonacci number. That would be good. That would be a long break. So here's an idea, right? Notice that when we're doing this calculation right here, we calculated the 3rd Fibonacci number. And we did a recursive call. We said find fib of 2, fib of 1. And these calls didn't have to recurse. Those are base cases. They each returned 1. So when we added those together, we got a 2. So at this point down here, we calculated that the value of the 3rd Fibonacci number was 2. Later on, we're going to come right here and we're going to again try to calculate the 3rd Fibonacci number. Instead of making these recursive calls, what if we just remembered that the 3rd Fibonacci number was 2? And the same thing over here, and the same thing over here. And by the same token, when we calculate the 4th Fibonacci number right here, we're going to notice that it's equal to 2 plus 1. Fib of 4 is equal to 3. What if instead of calculating that again over here and over here, we simply remembered this? And we said, hey, from this point forward, anytime you want the 4th Fibonacci number, it's just a 3. And so this is the idea of dynamic programming. We're going to basically cache values of our function as we calculate them, so that if we try to calculate the same value again, we don't. We don't have to go through and do the whole calculation in the whole recursive tree. We'll simply read a saved value out of a memory cache. So this is just caching of results. So here's how we can augment our Fibonacci function. I'm going to make a cache that I'm calling array to save fibs. Right? This is the array in which I'm going to save the values of my Fibonacci function as I calculate it. And I'm setting up enough space to store 1,000,000 Fibonacci numbers. We're not going to use all of those. And I'm going to initialize this array to have all zeros. Why am I doing all zeros? Because I know my Fibonacci numbers are always positive. And I want to know when I try to calculate the 4th Fibonacci number, have I already calculated it or not? So I'm going to initialize my cache to have all zeros. When I calculate a Fibonacci number, I'll save it in the array. Which means later on, if I look in the array, all I have to do is ask the question, is the number in this array a 0? If it is, I haven't stored anything there. But if the value in the array is not 0, I must have stored a number there, which would have been, you know, the Fibonacci number that I'm about to calculate. And so instead of calculating it, I'm just going to read it from the array. So how does this work in code? This initializes my array to be all zeros. And now I'm going to, you know, my main program, I'm going to loop 1,000 times and just call my fib function to calculate Fibonacci numbers in succession. So my Fibonacci function's almost exactly the same. If my argument is 2 or smaller, that's a base case, I just return 1. Otherwise, here's where I do my recursive call, add the 2 previous values, save that in F and return it. But I've added 2 extra statements to this, and most of the time, dynamic programming, you basically add 2 things to your recursive function. You add something before you do all the work, and something after you do all the work. Alright, so how does this play out? My number is not less than or equal to 2. It's not a base case. I would have to do this expensive recursion. Before I do that, I do one check. Check my cache. See if the nth element in my cache is positive. If it is, I know I've saved a value in there. That value should be the value of the nth Fibonacci number. I'm just going to return that. So I exit from the function right here. If I couldn't use the fact that, you know, a positive number meant I'd stored something, I'd have a flag or something like that. But somehow you decide, have I already calculated this value? Have I called fib with n before? And if I have, then the value should be saved in this element of the array. I'm just going to return that. But if I haven't done that, if I haven't called fib with n before, I've got to do this calculation. Right? I've got to do some kind of, you know, recursion here. And whatever happens after that, when I come back from this, f should be the nth Fibonacci number. So I'm going to return that, but before I return, I'm going to save it in my cache. So I stick f into element n of my array of saved values, and then I return. And so this saves the result of, you know, calling fib of n. And the next time I call fib of n, this will now say, hey, there's a number in here that's positive, and it'll just return it, and it short circuits this whole recursive process. So it's the same thing as our previous version, except we've got, you know, this extra check in the beginning, and then a way to save our value at the end. And so if we run that, 1,000 Fibonacci numbers, no problem. Right, and it overflows at 2 billion, but that's okay. And the only delay here is, you know, the time it takes to output. So if you just run it, it's more or less instantaneous. Is it really necessary to check for n bigger than 0? I don't think I do that. You mean this down here? So if I didn't do that, if I don't do that, all my Fibonacci numbers are going to be 0. Because that's how I know whether or not I have to recurse. And by initializing these things to you know, some kind of flag to say, hey, there's nothing stored in here, I can check that flag and know that, you know, the first time I try to find Fibonacci 5, I have to actually calculate fib 4, fib 3, and add them together. And these, you know, might end up actually making recursive calls also, or they might just read out of the cache. And then I'll save them at the end. If I don't do the save at the end, it still works, but it gets slow, right? Because I'm not saving any of my values, so I'm not actually using the cached values that I'm not actually saving the values after I calculate them. So it's the combination of those. That's the essence of dynamic programming. And so when you have a problem that this works well for, it's got these 2 characteristics, a recursive substructure and repeated subcases. So recursive substructure means we can think of the problem's solution in terms of the solution to subproblems. So divide and conquer comes to mind, right? We can take the problem of finding the nth Fibonacci number, and we don't have to write a loop or anything like that. It's really just a matter of solving these smaller problems and adding their solutions together. And all the problems that we're going to look at for this have that recursive structure to it. This idea that we can solve this big problem by solving, you know, a smaller problem, or maybe a set of smaller problems, and then combining those solutions in some pretty simple way, and that gives us the big solution. So that's one step, and that means we can use recursion. The other thing is the repeated subcases. The fact that, you know, in the process of generating the 7th Fibonacci number, we're going to calculate the 4th Fibonacci number a bunch of times, and the 3rd Fibonacci number a bunch of times. And by the time we're looking at the 100th Fibonacci number, we're going to calculate f of 7 a bunch of times, right? Huge number. And so the fact that we're repeatedly doing these same subcases, that's where we can use dynamic programming, which, yeah, is basically just remembering a calculated value to reduce calculation time. That's exactly what it is. All right, other questions about that so far? Yeah, we're going to do a bunch of examples of this actually next. And this will be where PA5 comes from. So PA5 will be, I'll give you a particular problem that dynamic programming works with well, and that if you don't use dynamic programming, it's really difficult to solve. And then you'll code up a solution to that. And the biggest challenge of PA5 will be simply, you know, sort of understanding the structure of the problem. Again, the actual code may not be all that much, certainly less than PA4 or PA3, but it's sort of getting the nuances just right. All right, so let's start with some examples. The first example is the knapsack problem. And there's a variety of knapsack problems. There's different versions of this. But here's the basic setup, right? So you know how sometimes stores have these promotions where, you know, you're the millionth customer and they you know, flash a light and there's a siren and confetti falls down and the manager comes out and shakes your hand and gives you a bunch of money or something, right? Because you're the millionth customer at the store. So sometimes, you know, for publicity, what stores will do to award a prize is they'll give you a shopping spree, right? And they're not just going to say, you know, go pick out anything you want from the store. So they have some kind of gimmick. So they might hand you a bag, right? And say, you know, fill this bag with whatever you want, and it's yours for free because you're the millionth customer. And so, you know, the cameras follow you around, you go around, you grab all your favorite things and put them in the bag until the bag can't hold anymore, and you go home and it's like Christmas Day or something, you know. So that's the basic setup for these knapsack problems, except, you know, that would be a knapsack instead of a bag, but we'll work with a bag. All right, so the question is, right, what do you put into your bag to maximize the amount of value in that bag? And forget about personal preference, right? If you really like gummy bears, don't fill your bag with gummy bears, right? Fill it with, you know, 16 terabyte hard drives, right, that you can sell and then get the money to buy gummy bears or something. So we want to maximize the value that you can put into the bag. Okay, that's the basic setup. And there's different versions of this. So if this is you know, a food co-op where all the food is, you know, in these giant bins and you just put a scoop in and scoop out how much you want, the algorithm is pretty simple, right? Assuming there's a bunch of bins, you can calculate the value of each thing in the bin. So maybe these are walnuts, and this is maybe $5 per pound. And here's you know, flour, and this is $2 per pound. And here's saffron, and this is $1 million per pound. And here's, you know, oatmeal, and this is $1 per pound. And let's say your bag holds 20 pounds, right? You can put 20 pounds worth of stuff in there. Yeah, so by value I'm talking about price, not aesthetics or anything. Alright, you got a bag that can hold 20 pounds. You've got 4 things you can choose from: walnuts, flour, saffron, and oatmeal. What are you going to put into your bag first? This is a life skill, you know. Are you going to put in 20 pounds of walnuts and walk away with $100 worth of walnuts?
If I was a walnut fan, maybe, but no.
If you're a walnut fan, yeah. Or if you feed squirrels, like some people. But you know, the saffron costs $1 million per pound. It's one of the most expensive, rarest spices on the planet, right? If you could get 20 pounds of that in your bag, you walk away with a bag that's worth $20 million, right? Think how many hard drives you could buy for that, right? So, you know, clearly in terms of maximizing your profit, your takeaway, right? You would put as much saffron as you had. Well, they probably don't have 20 pounds of saffron. They probably have, you know, like an ounce of it. But still, you would take as much saffron as you can and put that into your bag. And that would use up some capacity of your bag. So you've got some amount of that filled with this wonderful spice. And now, you know, you can choose from walnuts, flour, or oatmeal. Well, you know, if you take a pound of walnuts, that's worth $5. If you take a pound of oatmeal, that's worth $1. So you're going to take the walnuts and put those in your bag next. And if you can fill the rest of your bag with walnuts, that's great, right? But if there's only, you know, 10 pounds worth of walnuts, well, you know, you'll put 10 pounds in there. And you're still going to have, you know, almost 10 pounds left in your bag. Well, start taking the flour. And if you can fill the bag with flour, that's fine. And you just keep going like that. So for this problem where you can take a fractional amount of anything that you choose, right? The algorithm is simple. Find the item that's worth the most per weight and take as much of that as you can. And then if you've got more space left in your bag, find the next most valuable item and take as much of that as you can. And so this is appropriately called a greedy algorithm. And a greedy algorithm is one which tries to solve the problem as much as possible right now. Right? So greedy in the sense of not thinking down the road, not planning, not biding your time, just gimme, 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 right? So this is the really valuable one. Yeah, give me as much of that as you can, right? So these are greedy algorithms, and a lot of problems can be solved with greedy algorithms. And so this is a huge class of algorithms. No duplicates for PA4.
So just print out like error data for plate ID.
So you can assume the database will not have any duplicate plates in it.
You know, I'm asking like if the user wants to add, if the user tries to add. Great.
Your add function has no way to return that information, and the user can't add plates. Yeah, they just get added from the original database. Yeah, that's fine. All right, so greedy algorithms work well for some problems, and the fractional knapsack problem, where you're allowed to take, you know, less than whole numbers of items, greedy algorithm works fine. But there's another version of the knapsack problem, which is the integral, not like calculus, but like integers. So the integer knapsack. And here, you're not taking things out of bulk bins, right? You're picking items off a shelf. So I can take 1 pen or 2 pens or 3 pens. I can't take 1.5 pens. I can take 1 calculator or 5 calculators or 100 calculators, but I can't take 2.3 calculators. So with the integer knapsack problem, you have an inventory of items that you can choose from, and there's a value and a weight associated with each of them. And the question is, which item should you take, and in what quantities, in order to maximize your total value. And so here's an example of an integer knapsack problem. So let me give you an inventory of 3 items. So here's an item, here's the weight, and here's the value. So our first item is a pen, and it weighs 2 pounds. It's a really heavy pen, and it's worth $1. These are abstract units. All right. The next item is a phone, and it weighs 3 pounds, and it's worth $9. We're in some weird semi-parallel universe where economy is really strange. All right, the third item is a calculator, and that weighs 4 pounds, and it's worth $13. And the capacity of your bag is 10 pounds. And you're going on your shopping spree, and you're allowed to take any number of these that you want, as long as you don't exceed 10 pounds in weight. And your goal is to pick some set of items so that you maximize the value that you get out of that 10 pounds of storage. All right, so that's our setup. We're going to study this problem. Let's take a 5-minute break first, and we'll come back at, let's see, come back in 5.5 minutes. All right, and we'll start off with figuring out an answer to this problem. So play around with this on your own if you want for a few minutes.
so he'll see the note tonight, and he'll bring it home, and then she went through the whole, I feel like I know everything that happens now. Yeah.
Okay. Yeah, I have a credit card in there that I don't need to bill for.
Oh, excellent.
I found a problem with my old bow.
Yeah?
Yeah, I had a stray wire
Oh,
stuck
man.
underneath the processor,
Mm-hmm.
which was shorting out like, 7 pins or something.
Uh-huh. Just do that over there. I have not.
All right, let's see. So you have an unlimited number of these available to put into your bag. All right, so what do you think about this? Any shoppers ready to make a stab at it? So we can try a greedy algorithm and calculate the value per pound. And so the pen is worth $0.5 per pound, right? It costs $1, it weighs 2 pounds. Hey, I'm unmuted now. All right, so any ideas about this? We can calculate the value per weight. So the pen is basically, half a dollar per pound. The phone, $9, weighs 3 pounds. This is $3 per pound. The calculator, $13 for 4 pounds. So 13 over 4, this is actually $3.25 per pound. And so if we look at value per weight, the calculator is the most valuable, followed by the phone, followed by the pen. So what do you think our best solution is going to be? Three phones. So if we do 3 phones, that's 3 times 9 equals 27. That seems like a pretty good haul. If we do 2 phone plus 1 calculator, that's going to be 2 times 9 plus 1 times 13. That's 18 plus 13. That's $31. That's an even better solution. The greedy solution would say, let's put in as many calculators as we can because those are the most valuable. So we would have 2 calculators, and that would take 8 pounds, and then we'd have 2 pounds left, and the only thing we could fit in there would be a pen. And so that would be 2 times 13 plus 1 times 1. That's 27. That's not your best value. Your best value turns out to be this. And so you can't solve this with a greedy algorithm. The integer aspect of it breaks that. And you know, you do put a calculator in your bag, right? You get 4 pounds of your bag being used, you get $13 out of that. You've got an extra 6 pounds, but you need to ignore this more valuable calculator and go with the less valuable phones. Right? So this is perhaps counterintuitive. It's not a greedy algorithm that gets you the optimal. The greedy algorithm says, okay, now I've got, 6 pounds left. How do I get the most value out of that? Well, let's start with the most valuable thing. But it doesn't work in this case. You need to deliberately skip the most valuable item and start taking some of this slightly less valuable item. The reason being that if you take 1 extra calculator, you're only left with 2 pounds. If you take a phone, you're left with 3 pounds of capacity, and you can utilize that really well with this $3 per pound item instead of having to take the really cheap pen. So we need to do something different to solve this problem. And it turns out there's a nice recursive way to describe the solution to this. And it's going to have this repeated substructure, repeated subcase setup that's going to lend it well to dynamic programming. Okay, so we're going to talk a lot today and probably Monday about a pseudocode for a function I'm going to call maxval. And maxval is a function that takes a capacity and it returns a value. Yeah, 3 calculators won't work because that would weigh 12 pounds, which is too much. Alright, so maxval is a function that takes a capacity and returns a value. And we want to describe an algorithm for calculating maxval. So that in this case, if we called maxval with 10, it would give us back 31. Now we can do this exhaustively, right? We could take every possible combination of these items and pick the ones that, add up to less than or equal to 10 pounds and just calculate the maximum. That's a super expensive operation, right? The order of complexity of that is some huge geometric expression, so something with a big exponent, and we don't want to do that. We want an efficient algorithm to calculate the maxval. So this is, return largest amount for the given capacity. And we're assuming that, you know, we've got some inventory of items here. And so this might be, you know, weight, bracket, you know, some array, and here's some value array. And maybe this is a name array. And so we have an array of weights and an array of values. We're using parallel arrays here. So weight 0 is the weight of the first item. Value 0 is the value of that item. Name 0 is the name of that item. That kind of setup. All right, so how can we describe the maximum value we can get out of a bag with this capacity? And we're going to use the following slightly different way of looking at this. So let's think about the first item we put in the bag. All right, so I'm going to call this, you know, item 0, item 1, item 2. All right, so if you start with item 0, which is a pen. So you go into the store, right? You got this bag. You got to put something in the bag first. The first thing you're going to put in your bag is either a pen, a phone, or a calculator, right? The order in which you put these things in your bag doesn't matter, but you know you're going to put something in your bag. Otherwise, your total value is 0. And you only have these items to choose from. So there's going to be a first item you put in your bag. And it's going to be either a pen, a phone, or a calculator, item 0, 1, or 2. So I want to look at all three possibilities. All right. This is going to be a quirky algorithm, so ask questions along the way. So if you start with item 0, which is a pen, two things happen. The value that you get right now is the value of a pen. Right, I put a pen in my bag. Okay, I've got $1 worth of stuff in my bag. The remaining capacity is my current capacity minus the weight of the pen. In this case, the pen weighs 2 pounds, so I started off with 10 pounds. I've got 8 pounds left in my bag. I now have a new sub-problem. If I have a bag that can hold 8 pounds worth of stuff, how do I get the most value out of that? Some combinations of pens, phones, and calculators. But if I solve that problem, if I know how to get the most value out of a bag that holds 8 pounds, I can add that to the value of the pen that I already put in my bag. That's the maximum value I can get out of my bag if I start with a pen. So maximum value possible for the remaining capacity well, how do I calculate that? I'm going to use my maxval function. So I'm going to calculate maxval of my original capacity minus the weight of my pen. And if I take my original value of the pen and I add the maximum value that I can get out of my slightly diminished bag, that's the total value that I'll have out of my bag. So if I start with item 0, if I put a pen into my bag, the best I'm going to do is I'm going to end up with the value of the bag plus whatever the best is I can get out of a bag that holds 8 pounds. So that's one possible outcome. If I put a pen in my bag, this is the most that I'm going to get out of my total 10-pound bag. But if you start with item 1, which is a phone, my value is going to be the value of that phone plus the maximum value of the original capacity of the bag minus the weight of the phone. And if you start with item 2, which is the calculator, then the maximum value I'm going to get is the value of the calculator plus whatever value I can get out of the remaining capacity of the bag, which is the capacity of the bag to start with minus the weight of the calculator. Whichever one of these is the largest, that's the value of max val for the given capacity. Alright, this is the entirety of PA5. This is all it's going to boil down to. To find the maximum value for a given capacity, you're going to put some item in to begin with, either item 0, 1, or 2. And that's going to do two things. One, it's going to give you the value of that item as part of the total value you've got. And two, it's going to leave you a bag that holds a little less, the original capacity of the bag minus the weight of item 0, 1, or 2. And we can use our max val function to find the most value we can get from that diminished bag. And if we add that to the value of the item we just put in, that's the best value we can possibly get if we start with that item. So if we start with a pen, this is our maximum value. If we start with a phone, this is our maximum value. If we start with a calculator, this is our maximum value. Whichever one is largest, that's the best maximum value we can get out of this bag. And that will be the value of the max val function. So we'll run through this with some numbers in a second, but any questions up to this point? Alright, so let's calculate max val of 10. I haven't tried this before. I don't know if this is going to work or not. Alright, so there's three possibilities. If I put a pen in, so this is going to be the largest of the following three possibilities. If I put a pen in, it has a value of 1, and it leaves me with 8 pounds of capacity in my bag, so it's 1 plus whatever the maximum value of 8 is. If I put in a phone, that gives me a value of 9. It weighs 3 pounds, that leaves 7 pounds in the bag, so it's 9 plus max val of 7. And if I put a calculator in, that gives me $13. It weighs 4 pounds, my bag starts with a capacity of 10. If I put 4 pounds into my bag, it can hold 6 pounds, and the most I'll get out of that is whatever max val of 6 is. So max val of 10 is equal to one of these three numbers, whichever is largest. 1 plus max val 8, 9 plus max val 7, or 13 plus max val 6. Well, we got some recursion to do, right? So what's max val of 8? Well, again, it's the largest of three possibilities. Either put in a pen, which weighs 1, and leaves me with a total capacity of 6, so it's 1 plus max val of 6. Or put in a phone, which is worth 9, weighs 3 pounds, so that leaves me with a capacity of 5, so 9 plus max val of 5. Or put in a calculator, which gives me a value of 13, and leaves me, 4 pounds taken out of 8, leaves me with a capacity of 4. And so whatever max val 4 is, right, add 13 to it. So whichever one of these is largest, that'll be max val H. Well, we got some more recursion to do. Let's calculate max val of 6. So if I put in a pen, it's worth $1. It weighs 2 pounds. That leaves 4 pounds in the bag, so it's 1 plus max val of 4. If I put in a phone, that's worth $9. It weighs 3 pounds, leaves me a capacity of 3. And if I put in a calculator, that's worth 13. Weighs 4 pounds, so that leaves me a capacity of 2. Everyone following this? Any questions? What the heck we're doing here?
If any questions come up, I'm sure they'll come later.
Okay. So let's keep recursing. Let's find max val of 4. So we have a pen which weighs 2 pounds, so it's 1 plus max val of 2. We have a phone that weighs 3 pounds, so it's 9 plus max val of 1. And we have a calculator which weighs 13 pounds. The calculator weighs, sorry, it's worth 13. It weighs 4 pounds. Our bag holds 4 pounds. So if we put a calculator in, the remaining capacity in our bag is 0. Our bag is full. We're going to have a base case. The base case is max val of 0 equals 0. If you can't fit anything in your bag, you can't get any value out of it. So this case we're not going to have to recurse for, but we're still going to need max val of 2. So let me move across my page. So max val of 2 will be the maximum of, and I can put a pen in. A pen is worth $1. It weighs 2 pounds, so that will leave me with a capacity of 0. And that's the only option. If my bag holds 2 pounds, I cannot put a phone in it, because the phone weighs 3. If my bag holds 2 pounds, I cannot put a calculator in because the calculator weighs 4. So the only option for a bag that holds 2 pounds is to start off by putting a pen in. That'll give me $1 back plus max val of 0. All right, max val of 1. Well, I can't put a pen in, I can't put a phone in, I can't put a calculator in. Right? I'll go through this sort of thought process of, trying to put each item in as my first item, but I will discover that each of those items is too heavy for the bag. And so I have nothing I can calculate the maximum of, and so max val of 1 will just turn out to be 0 also. So this is a base case. This we always know. This we discover because when we go through our inventory, none of these fit. If we had an item that only weighed a pound or weighed less than a pound, we could fit that in and continue. But since none of these will fit, we'll end up, calculating the max of nothing. Max val of 1 will be 0. Well, now we have enough data to actually complete these recursive calls. Because max val of 2 is equal to 1. So 1 plus max val of 2 will be 2. 9 plus max val of 1 will be 9 plus 0 is 9. And 13 plus max val of 0 will be 13. And so this will be 13. So we know max val of 4 is 13. Well, we still need to find max val of 3. So let's do that. And I think this is the last one we have to do for a little bit. So max val of 3, if we start off with a pen, that's worth 1. It weighs 2 pounds. It leaves us with 1 pound of capacity. Or we could start off with a phone, which is worth 9. Weighs 3 pounds, leaves us with a max val of 0. Well, this will be the maximum of 1 plus max val of 1 is just 1. 9 plus max val of 0 is 9. This will be 9. Alright, now we can find max val 6. It's going to be the maximum of 1 plus max val 4, which is 1 plus 13 is 14. Or 9 plus max val of 3, 9 plus 9 is 18. Or 13 plus max val of 2, 13 plus 1 is 14. The maximum of those is 18. So right now we know if we have a bag that holds 6 pounds, the best value we can get out of there is 18. And it turns out we get that not by doing a calculator and a pen, which would give us 14, but by doing 2 phones. So we've already solved a subproblem that doesn't work with a greedy algorithm. Right? The maximum value we can get out of a 6-pound bag is not a calculator, the most valuable item, plus a pen. It's 2 of these medium items, 2 phones. All right, and so we can go on with this. So we can calculate 1 plus max val 8. Well, we need to know max val 8, and to do that, we're going to need max val 5. And to do this, we're going to need max val 7. And so we would need to do some more calculations, and these are going to be, you know, more recursion. We can do it, but it's, you know, more pages of paper. I don't think there's great value in doing that unless people have no idea what's going on here and we want to go through these other calculations in some different way. So let's look at this in pseudocode. So we're trying to find max val of some capacity. So we simply return the maximum of a series of calculations, where the calculations are, for example, value of item 0 plus max val of capacity minus the weight of item 0, value of item 1 plus max val of the bag's capacity minus the weight of item 1, and so on up to whatever our last item is, the value of that item plus the maximum value we can get out of our bag when we reduce the capacity by the weight of that item. So pseudocode, it's a one-liner. So the important part at this point is thinking about the recursive nature of this, the idea that we're breaking our problem into sub-problems. Right? If we want to find max val of 10, we find that by calculating max val of 8, 7, and 6 in this case. And depending on what your inventory looks like, what the weights and values of your items are, right? This could be, you know, 3 cases, it could be 300 cases. It depends on your inventory. But the essence is, right, this is saying, suppose we start with this item. Well, it's worth this much, and we can get some more value from our bag. Our bag doesn't hold as much as it did. It holds this much less than it originally held. And with this new capacity to our bag, this tells us how much money we can get out of that capacity, because that's what the max val function does. And so if we add that maximum value to the value of the item we put in the bag, that tells us how much value we get by starting with that item. And since we're going to start with one of these items, we calculate the value for each of those cases and we pick the largest number. That's the maximum value we can get from the original bag's capacity. So questions? We're down to 8 people in here, so it's a heavy burden on a small number of people to ask questions. But if you got questions, ask them. All right, let's talk about implementation details. This is great. We're going to be done with PA5 before the week's over. Implementation details. So how do we actually do this? Because we don't know what n is. We don't have a max val. It takes a bunch of arguments and so on and so forth. So you're going to do this with some kind of loop, right? So you know, have some current max that's equal to 0. And then, you know, for I equals 0 to, you know, largest item index. So if you got 10 items in your inventory, you're going to go from 0 to 9. And calculate if the value of item I plus max val of your capacity minus the weight of item I. Let's call this temp. Temporary value equals the value of item I plus the max val of a bag with your original capacity minus the weight of item I. And so if T val is bigger than current max, set current max equal to T val. So it's like a running maximum. So this does the effect of what I'm doing up here in pseudocode, right? For each of these indexes of possible first items, we calculate this expression, and if it's bigger than the largest thing that we've seen so far, just remember that new largest value. And when we're done with this loop, you know, just return current max. With one caveat, which is when we're going through and we're calculating these max vals. For example, when our bag only held 2 and we were trying to find max val of 2, we did not do 9 plus max val of minus 1 or 13 plus max val of minus 2, right? We only did 1 plus max val of 0. This calculation, right, value of an item plus the max val of a bag with diminished capacity, this only works if this is not negative. In other words, we're not allowed to calculate a possible maximum value by putting in an item that's too big for our bag. And so we need a special check in here. So if the weight of item I is less than or equal to the capacity, then we go ahead and we do all of this stuff. But if item I weighs more than what our bag can hold, don't calculate this tentative value and compare it to your maximum and add it. You'll get a bogus answer. And then we also need a base case which says, you know, if our capacity equals 0, return 0. So if our bag can't hold anything, there's no value we can get from putting things in that bag, return a 0. Otherwise, you know, set a current max and loop through each item. If that item fits in the bag, take the value of that item, add the maximum we can get from the remaining space in the bag. And if that total value is bigger than the maximum we've seen, save that as our new maximum. And when we're done looping over all the items, return whatever the largest maximum is that you found. And this translates into C almost directly. Right? This is just a recursive call, and these are arrays and so on and so forth. So it's got the structure of, you know, breaking a problem into subproblems. And each of these subproblems will be smaller than this problem, right? The capacity that you're passing to maxval will be smaller because your items weigh something. If your items don't weigh anything, right, you can take an infinite number of that item and get an infinite capacity. And if your items have negative weight, this does not work either, right? So if there's helium balloons in the store, there's no limit to the value you can get out of your bag. Right, put in 20 pounds of laptops and then put in 20 pounds of, you know, lift worth of helium balloons, and now you've got 20 pounds capacity left, and go on. So this is, you know, assuming the weights are positive, which means each of these is going to be smaller than the capacity. So solving a problem with, you know, capacity of n is reduced to solving a problem with arguments smaller than n, and then combining those solutions in some way. So it has that recursive structure, but it also has the repeated subproblem, right? So max val of 4 we calculate here and here, and max val of 2 we calculate here and here, and if we write out max val of 7 and 6, we'll see lots of repeated subcases. And this thing just blows up in terms of the amount of work if you don't do dynamic programming. You end up just calling the same values over and over and over again, and your program will take, you know, a few hours to finish on a really simple test case. So here we're going to use dynamic programming, and our maxval function, we're going to put a cache in, and in the beginning of this, we're going to check our cache. And we'll probably have an array that's indexed by capacity. Maybe initialize it to -1, because we should never have a max val of negative anything. And so in the beginning here, when you're asked to find max val of capacity, check that element in your cache. If it's negative, we haven't calculated this yet. So we need to go ahead and do all of this work and do our calculation. And then at the end, save your answer in the cache. And then return it. And then the next time that you try to do the same max val with the same argument, you'll check your cache, you'll see a number in there, and you'll say, oh, I've already calculated this, and you return it from the array. Alright, so that's going to be PA5. You're going to write a program that will take in an inventory of items with a weight and a value for each item. And you're going to write a maxval function, and then make a main program that lets you specify the total capacity of your bag and figures out what the maximum value is that you can get out of that bag, and also tells you what combination of items you should put into your bag in order to get that maximum value. And we can talk about tracking the inventory next week. But basically, you know, as you go through here, if you discover that, you know, this is the combination that gives you the maximum value, you need to record somewhere that, hey, the current maximum value that I have, not only what that number is, but that it includes, you know, one of item 1, plus whatever combination of items corresponded to this maximum value. And so you're going to need to do things like return a structure that can store an inventory, and your inventory can just be an array that says, how many of each item do I have, but you're going to have to start passing around more complex chunks of data, so structures. And other than that, it's pretty much just this. So I'm going to try to post PA5 sometime in the next few days. We'll definitely go through it on Monday, but you've got the bulk of it right now. We'll just go through kind of the details of exactly what your main program should do and any specific requirements. But that's basically PA5. So we'll definitely go through that Monday. I'll try to post it sometime before Monday, so you can get started on that. But let's go ahead and look at some other examples of problems that work well with dynamic programming. So another classic example is rod cutting. And rod cutting, you picture that you have, a bar of some kind of material. And let's say this is, 12 inches. And you have the ability to cut this rod into different size chunks. So let's suppose you have, 1-inch increments. And it turns out that, in the open market for cut up pieces of rods, not all lengths are worth the same amount. So there's, a cost of material. 12 inches of rebar costs a certain amount just because, it's material, it's got value to it. But it turns out that certain lengths might be more usable to people than others. And so you can have a pricing table of what you can sell different lengths of this bar for. And so a 1-inch piece might cost, $2. A 2-inch might cost $4. But a 3-inch piece of rebar might be a really, really common size. And rather than being worth $6, that might actually be worth $9. And a 4-inch piece might be a size that nobody ever uses, and so maybe this is only worth $1. And a 12-inch piece, which is totally uncut, maybe that's too long for people to use, and so maybe this is only worth $20. And so the question is, if you have this bar that's 12 inches in length, how should you cut it up in order to be able to sell it for the most amount of money? And I could sell it as just a 12-inch bar for $20. I could sell it as a bunch of 1-inch bars for $2 each. That would be worth $24. That's worth even more than selling it uncut. I could cut it into 4 3-inch segments and get a whopping $36 out of it. I could cut it into 3 4-inch segments and I'd only get $3 out of it. And so depending on what this pricing table looks like, right, how do you maximize the value of this? And it might be that if I cut it into a 4-inch segment, right, I get $1 out of that, but maybe an 8-inch segment is really, really valuable to people for some reason. If there was an 8-inch length and that was worth $50, well, I would go ahead and I'd cut 4 inches off, sell that for $1, but then I'd have the 8-inch piece that I could sell for $50. That might be my best solution. So how do you find that? And again, a greedy solution is not going to be the best option. It may be that I need to give up the most valuable length and not sell any in that size, because by picking some less valuable length, I have enough pieces left that I can cut some other more valuable pieces and end up in a better situation. And so we can look at this as another max val function. And so max val of some length, and it's going to be, the cost of a 1-inch piece plus max val of the remaining 11 inches, or the cost of a 2-inch piece piece plus the max val of a 10-inch piece remaining, or the cost of a 3-inch piece plus whatever I can get out of the remaining 9 inches, or the cost of a 12-inch piece plus what I get from a 0-inch piece, which presumably is 0. And so it would be, the maximum of these 12 possibilities. And so this is extremely recursive. Right, to calculate max val of 12, I'm going to end up making 11 recursive calls. To calculate max val of 11 is going to be 10 recursive calls. Max val of 10 is going to be 9, and so on. And then I'm going to have to calculate max val of 10 again, and so on. And if you add this up, it's a huge, geometric formula. But recursive substructure and then common repeated subproblems. This works well with dynamic programming. And in this case, we know that we're going to calculate the max val of a 1-inch piece of rod, right? And then use that to calculate max val of 2, and so on, and so we can kind of work our way up. With the knapsack problem, there's some capacities we're probably not going to calculate, right? We're not going to need to calculate max val of 9. It just doesn't come up in the solution. And so we don't want to just, start calculating the max of, every possible length. We want to do it sort of more strategically by doing it as we need to calculate these, by following, this kind of repeated substructure. So questions?
Is this a same algorithm that programmers typically use for many of these dynamic programming problems that they face?
Sorry, say that again. Same algorithm as what?
Do they use this kind of algorithm for many of these dynamic problems? Is there kind of like a formula that they use?
These are pretty typical problems that dynamic programming lends itself to well. You can actually pull up some good lists. Let's take a shot and see what we got here. Top 20 dynamic programming interview questions. So longest common subsequence. Oh, don't give me this. Longest common subsequence, longest increasing subsequence, minimum partition. There's the 0-1 knapsack problem. There's rod cutting. There should be egg dropping. We'll talk about egg dropping on Monday also. These are all pretty classic problems that that lend themselves well. Dynamic programming basically kicks in any time that you're using recursion, but your recursive path involves, repeating your work over and over. Dynamic programming is a way to avoid repeating that work. So that's the whole idea of caching the results along the way. We might talk about this one next week also. So optimal substructure and overlapping subproblems, same idea. Recursion is a convenience sometimes. If you can think of your problem in a different way, if you think of, finding the height of a tree recursively, it's a lot less work or at least a lot more straightforward than trying to, you know, start at the root of a tree and move down and keep track of whether you're going left or right and which branches haven't you followed yet and so on. The recursive version of, say, the height function is much more straightforward, right? Find the height of the two subtrees, add one to the largest. And so recursion sometimes is easier to define an algorithm if we allow a recursive algorithm. It's also sometimes easier to code because, you know, you don't have to loop, you don't have to keep track of stuff, you're just making recursive calls that match whatever the algorithm is. But a lot of times recursion ends up being more expensive time-wise, and sometimes more expensive space-wise. And so if you want to, this is my introduction to recursion. Ackermann Function is an extremely recursive function. It was developed, I believe, purely as a theoretical thing, and it can only be defined recursively, I believe. And so it's a function of two arguments, so I and j. And if I is 0, then Ackermann 0, comma j is just j plus 1. That's easy. If j is 0, Ackermann I 0 is Ackermann of I minus 1, comma 1. And the general case ij, Ackermann ij is Ackermann of I minus 1, comma Ackermann I, comma j minus 1. And so, you know, it's clearly recursive. And so if you want, you know, Ackermanns of 3, comma 3, that would be just Ackermann of 2, comma Ackermann of 3, comma 2. And so Ackermann of 3, comma 2, which is this part right here, would be just A of 2, comma A of 3, comma 1. And this part right here, A of 3, comma 1, would be Ackermanns of 2, comma Ackermann 3, comma 0. And Ackermann 3, comma 0, we get to use this case up here. That's just Ackermann's 2, comma 1. And so this is very easy to code, right? It's 3 statements. If I equals 0, this. If j equals 0, this, else this. And it's super easy to code that in C, but it's a shocking function in terms of the values that you get for this. So let me find you some numbers. All right, so this thing grows up. So A4, comma 2, for example, is a number with almost 20,000 digits to it. Right, this thing just grows really, really quickly. And it's a nice example of how, you know, something that looks fairly benign in terms of recursion can entail a huge amount of work, right? And it's studied partially as a way to study large numbers, so or huge numbers, and numbers that get so big, right? So here's Ackermann 4, comma 3, and you know you can go through the first few calculations of it, and if you keep doing this, it ends up, you know, 2 to the 65 536 minus 3. And so people have developed new ways of writing numbers that make it possible to write big numbers like this without having to have lots of exponents. And so you can get into this Knuth notation with these arrows that represent just tremendously large numbers. And there's a whole number of areas of study related to just the study of large numbers, where large is not, you know, like a million or a billion, but like something that we can't even write in this form without introducing new notation for describing ridiculous exponents. So what were we trying to do? 3, comma 3. So that doesn't help us. So that's a fun function to play with. And it's been studied for like 100 years or so. But you know, super trivial to write. You can code up a C function to calculate this. All right. Well, if there's no questions, I'm going to call it quits here, because that's 12 o'clock. So finish up PA4. Make sure you get that submitted. If you can't get the delete function to work, right, make sure your other functions work. Make sure your program doesn't just segfault or refuse to compile or something like that, right? Go back and think about the grading. And if you have to comment out the delete function, you know, you can put a submission comment that says, hey, I almost got delete working, you know, that kind of thing. But make sure that what you submit runs as well as it possibly can. Get that turned in by Friday. I'll get it graded over the weekend, hopefully, and I'll get PA5 posted, and we'll dig into specifics of that on Monday. All right, that's all I got for today. I'll see you in 2:15, or I will see you next time.
I
See ya.